Okay, guys. Okay, so good afternoon, everyone. So I just had the exam yesterday. I hope that it was not too stressful. Today, I was supposed to give you some hints for assignment 5, which is due Friday. So instead of making that its own video, we'll just go through those couple questions today. And then I might as well also just go back to the proposition which was confusing me on Monday and just tidy that up. And then those two things might take up the entire class, but if it doesn't, then we have a little bit more time. That's okay. And we can work on something else. Also, at the end of class today, I'll give you a link for just a little, kind of a questionnaire. It's just something I'm trying out. So, if you want, you can answer the questions. And that is helpful for me to see what's happening. Okay. So let me first go to the assignment 5, which is due on Friday. And I know you just had an exam, which is why I wanted to give you a healthy amount of hints for this assignment. Okay, so that it's not too stressful. Assignment 5. Okay, so in this assignment, so if you remember back when we were doing the real numbers, the first thing we did was when we defined the real numbers as a set of all Dedekind cuts, and then pretty much one of the first things we did was, we proved things like that, the real, we define less than for real numbers. But one of the first hard things we did was prove that every non-empty bounded subset of the real numbers has a least upper bound. Okay. So for this assignment, we're using that fact, to define addition and multiplication. Okay. So behind everything, we have this fact called the least upper bound property, which we proved. That if S is a subset of the real numbers, S is non-empty, and S has an upper bound, under those conditions, and S has a least upper bound, and we call that the soup. We just call it soup of S for supremum. Okay. So that's hiding behind everything why we can do this. Let me make sure. Okay. And then so for question 1, it says we're supposed to do questions 1 and 2. Sure. For question 1, we define A plus B as the soup of some set. Well, it's going to be the soup of the numbers P plus Q, where P and Q are rational numbers, and P, we'll say it's less than or equal to A, Q is less than or equal to B. Okay. So for this question, we're not really, I mean, you can check that this is well-defined, et cetera, but we're not worrying about that. For this question, we have to prove like A plus B equals B plus A. And this is just to, oh, I'm sorry, yes. Okay, sorry for leaving you guys outside. Okay, let me make sure I don't do that. Here we go. And thank you for telling me to let everyone in. Okay. So as I was saying, I'm not worried about proving that this addition is well defined. I mean, certainly that's not that bad to do, but we're just going to prove that for this question, we have to prove A plus B equals B plus A, maybe just as a kind of to convince ourselves that it's kind of like a routine calculation or something. Okay. So first of all, A plus B, well, that's just the soup of P plus Q where P is less than or equal to A, Q is less than or equal to B, P and Q are rational. Okay, and so why is that important? Well, because we already know how to add rational numbers. Okay, so we take all the rational numbers less than A and add them to all the rational numbers less than B, add them, okay, and the least upper bound of that set, that's the definition of A plus B. And so how do we do it? Well, if we have P plus Q, addition of rational numbers is commutative, so this is the same as Q plus P. Such that, well, Q is less than or equal to B, P is less than or equal to A, P and Q are rational. And notice, this is just a definition, like this is the least upper bound of things less than B plus things less than A. In other words, this is just the definition of B plus A. Okay. So that's all I'm looking for question one. Okay. I guess I need to add in like some justification. The main justification I need is that since P plus Q equals Q plus P for P and Q in the rationals. Okay. So this is just like a kind of a routine thing. And you know, a similar thing, so you can kind of guess that a similar thing is going to happen for things like proving that 0 is the additive identity, or proving that negatives exist, like additive inverses exist, and so on. You know, okay. So for question two, it's a little bit more tricky, but still not bad. So I just want to talk a little bit about that too. So for question two, we have two positive numbers A and B with A less than B, and X is positive. And we have to prove that AX is less than BX. Okay. A familiar, you know, inequality. You know, if you ever have to solve inequalities, you often use this. Like, for example, if you want to solve a half X less than 5, well, you have to be able to multiply both sides by 2. You multiply by 2, and then you get X less than 10. You know, pretty simple. If we don't have this property, though, we can't even solve this simple inequality. Okay. So let's try and prove this inequality and convince ourselves that it's like not that bad. For this proof, we have to know what the definition of A times B is, at least for positive numbers A and B. So recall that in this situation, well, really, I just give you the definition in the question. We'll say that AX is going to be defined to be, let's say, Q times S, where Q is less than or equal to A and is positive, S is less than or equal to X and positive, and Q and S are rational. Okay. So take and we take the soup of that, right? So multiply all things that are less than A to all things less than X and take the least upper bound. That is what we call A times X. Okay, it's only, we restrict to positive things because we have to do a little bit more work when the numbers are negative, but it's like once you define it for positive numbers, you kind of go from there. Okay, so using this definition, we have to prove that AX is less than BX. Okay, and what else we have to use? I'll just write down another fact we need. Recall also this is something we proved in class. If since A is less than B, there exists a rational number T with T in between A and B. Okay. Okay, and we have to show that AX is less than BX. Okay. Okay, so proof or a solution, I guess. Suppose R is a rational number and 0 is less than R is less than X. Okay, and our thinking is, oh, no. Sorry. First, let's just write down what AX and BX are. AX is the soup of the Q times S's such that Q is less than or equal to A, and S less than or equal to X. Q and S are rational, and BX, that's another supremum. We'll write it as QT. Oh, sorry, we'll write it as RS, yes. Okay, and I don't have to use the same letter for S in either one, but I do so to kind of suggest something. R and S are rationals. Okay, we want to prove that AX is less than BX. Well, certainly, if I fix S, right? Okay, so let's look at a typical element of this set and prove that it's less than some element over here. Okay, so let Q be such that 0 less than Q less than or equal to A. S be such that 0 less than S less than or equal to X. And there exists T such that, so Q less than or equal to A. So we can find our T in between A and B. So where T is less than A, or sorry, greater than A, but less than B. And T is a rational number. Okay. Now, so Q is less than T, therefore QS is less than TS. For all 0 less than or equal to X, S between 0 and X, and for all Q less than or equal to A, where S and Q are rational. Okay, so what does that tell us? That means like everything here is less than some element here. Okay. Okay, that means that this TS is an upper bound for this set. So that tells us TS is an upper bound. For those QS's where Q is less than or equal to A, S is less than X, Q and S rational. Okay, so if it's an upper bound, the least upper bound is less than or equal to TS. So that tells, well, AX, that's the least upper bound by definition. That's how we define AS. So by definition, the least upper bound has to be less than or equal to the n upper bound. We have AX less than or equal to TS. Well, that is actually not quite true. Because it's not an upper bound for all of these. It's only an upper bound if we eliminate this quantifier S. Okay. Yes, that makes more sense. So TS is an upper bound for all the QS's where Q can be anything between 0 and A. So so what we can do is we can just take the soup over S. That is our plan. So we can look at TX, or sorry, so we can look at this set, Q, the Q times S's, where Q is less than or equal to A. We can look at the soup. We can show that's equal to A times S. Okay, so TS is an upper bound for this set, so therefore, so TS is an upper bound for here, so AS is less than or equal to TS. And this is true for all 0 less than or equal to S, less than or equal to X. Okay. Okay. And what we now want to show is that you want to use this. So you want to show like the soup of AS where this is AX. Well, the soup of those is going to be less than or equal to the soup of TS. And that's just going to be TX. And then we want to show that TX is strictly less than BX. Okay. Okay. Okay, and the idea to do this would be to show that first, we know that TS is going to be strictly less than BS for all rational S. It would be, our idea would be to show something like that. Okay. Then if this was true, we should be able to show that it's still true when we take the soup. Okay. Okay, so how do we show that TS is less than BS? So BS is like the supremum of some set. So we just have to show that TS or it's the least upper bound, right? To show that it's less than the least upper bound, we just have to show that there's something in the set defining BS which is strictly bigger than TS, you know? Okay, so we find actually the further I go with this, the further I think that like maybe I'm just making it too complicated and there's probably like a much simpler solution. So I feel like I will just do this. I will just write up some solution for question 2. And you don't bother, you guys don't hand in question 2, just hand in question 1. Yeah. Okay, and then it'll be my job I just would like to find a simple, easy solution for this. Okay. Yeah. This was supposed to be like more on the easy side of things. So I feel like it's getting away from that. So yeah. Okay. The other thing so watch out for that. There's some typed up solution of this like certain proposition. It shouldn't be so bad once I just can sit down and work it out. Would that question be in an exam? Well, once I go to the trouble and actually like write up some solutions for it, it could possibly. Yeah. Okay. I also wanted to go back to this problem on Monday. Just have a few minutes. So let me just try and here is our situation. We had this like proposition or something. We're trying to show that if X is a proper subset of N, then there's no one-to-one F from N to X. Okay, and in our proof, we're doing it by induction, the base case, like trivial, et cetera, et cetera. Then I'll just put dots. And then we are in the induction steps. We were assuming that if X is a proper subset of N and okay, if X is a proper subset of N, then there's no one-to-one F from N to X. We have to show the same thing is true for N plus 1. Okay, so now assume, okay, for a contradiction, assume F goes from N plus 1 to X, where F is 1-to-1, and X is a proper subset of N plus 1. Okay, and then with the proper selection of your cases and stuff, you can dispense with this. So there's 2 cases. Either X is a subset of N, and the other case, well, if X is not a subset, X is a subset of N plus 1. So if X is not a subset of N, it means that N has to be an element of X. So the other case being that N is in X. Okay, that's the other possibility. Anyways, if X is a subset of N, okay, then we can just look at the restriction to N, and that goes from N to X, but without F of N. Okay. So if we restrict f to n, so remember that n plus 1 is just n union the singleton of n. Okay, so we're saying that here we're saying that either x is contained all in here or x has n in it. Okay, and now we're saying that in the case where x is completely contained in n, restrict f to only this, and then that is a one-to-one function from n to x, but without this f of n. So then f is one-to-one because it's a restriction of a one-to-one function, and x minus f of n is properly contained in x, which is contained in n. So x minus f of n is a proper subset of n. This is a contradicting the induction hypothesis. Okay. Now we have to deal with the other case. Okay. The other case is when n is in x. Well, then we can't really do this trick because this is not necessarily going to be a proper subset of n. This might include n and not be a proper subset of n. Okay, so we have to do like some kind of trickery. Not really trickery, but like something else. Okay, but what we know is that we can write n is equal to f of k. Okay, if not, let x prime just be x minus n. Then f is also going from n plus 1 to x prime, and now x prime is contained in n. Okay, so this problem, this second case, we only need to enter this case when n is equal to f of k for some k. Oh yeah. So what k can it be? It needs to be a k in some k in n plus 1. Okay, and then we do like a kind of a switch to try and construct a one-to-one function from n to like some set x. Okay, so now we define g from from n to what? So from n to something, let's see what. Okay, let's define g first and let's see what it is. So we define g of I to be f of I if I is not equal to k and I is less than n. And we write when I equals k, we just define it to be f of n if I equals k, which is less than n. Okay, and then what is g? So what happens is, I'll try and draw a picture. Here's n plus 1. N plus 1, the elements of n plus 1 are 0, 1, 2, all the way up to n. Okay. And then we have a proper subset of n plus 1 on the other side. Okay. And then, so f goes from like here to here. And what we're saying is that k gets mapped to n by f. Okay. And then n gets mapped to somewhere else, f of n. Okay, and we're leaving everything else the same, except instead of doing like this crisscross, we're mapping k to n. Sorry, we're mapping k to f of n. So instead of going down here and up here, we're just changing it like this, and then we're xing this off. Okay, and everything else stays the same. And so as long as our original function f was 1-to-1, we still have a 1-to-1 function. But now, there's our subset on the right-hand side is now going to be, doesn't include n, so it's going to be a proper subset of n. Okay, so notice that now the range of g has just replaced is just x minus n. Okay, and this is a proper subset of n as long as x is a proper subset of n plus 1. And notice g is 1-to-1. Okay. Okay, actually that took a long time. In the last 15 seconds, please everyone click on this link before it disappears. There's only 10 seconds left, and then fill in the questionnaire if you want. Okay, so that's it for today.